Yeah, they should be ready. They get ahead of time. And without any further ado, the man who needs to stop playing with DNS, Dan Kaminski. Give him a huge round of applause. Thank you.
Hey, guys. Dear God, this was one hell of a year. Hey, everyone. It's great to be here. This is, I think, my 5th CCC. Every year I always have such a warm and excellent time here. It's just an honor to be asked to come out to speak. So, how many of you guys have seen video or slides of the talk I gave at Black Hat? Yeah, that's not this talk. If you haven't seen that talk, hopefully you won't be too confused. But I was actually talking to the CCC guys, and they really wanted to hear, there's been a fairly ridiculous amount of press on all of this. They really wanted to hear less about what the actual bug was, and more about, so what the heck have you just spent the last year doing? Because we all know it didn't take that long to find the bug in the first place, and that's actually true. So this talk is much more about the larger scale lessons to be learned from the experience of attempting to repair a critical piece of critical infrastructure. So what are we here to do? We're here to do 4 things. We are going to quickly recap what the flaw was and the scope of things that it affected. We're going to analyze what forces allowed. This shouldn't have mattered. DNS shouldn't have been this significant. And yet, as I explored all of the various things that were using DNS, it just struck me. This is ridiculous. Why are this many security-sensitive decisions being made on something that has never taken a security dependency in its design? We'll talk about how this issue actually got fixed and some of the tales of those 6 months. I think the quote from Paul Vixie was, "I just spent 6 months trapped in a well with Dan Kaminski, and, well, it's nice to be free now." And the 4th thing we're going to talk about is DNSSEC, which is, believe it or not, might actually not be a bad idea. So, let's talk about the flaw. The flaw indeed originates with Dan J. Bernstein, who pointed out in 1999 that the 16-bit transaction ID in DNS, yeah, that's probably not enough. Okay, DJB was totally right. And the response he got back, what eventually the DNS community convinced themselves of, was that, yeah, 1 out of 65,000 isn't very long odds. But maybe we can make it so you can only play those odds like once an hour, once a day. And like 32,000 days is a really long time, so maybe we don't need to completely top to bottom, re-engineer the protocol or do any kind of these crazy fixes that are going to make things slow. You know what? It was 1999. People were a little naive back then. And yet, if you actually look all the way forward through 2008, this TTL strategy was about 1 draft away from becoming a RFC called forgery resilience. People really believed this TTL stuff was enough to stop DJB. They were wrong. They were totally wrong. People talk about the Kaminski attack as if there was one attack. Yeah, there's like 15 different reasons why that entire philosophy was wrong. There's just so many different ways to, instead of only being able to run the attack once a day, so you have to wait like, 83 years, yeah, you can run the attack a couple thousand times a second, so you have to wait, 5 or 6 seconds. It's not like 1 or 2 ways. It's really a lot. The only other thing I maybe figured out was that because the attacker controls when the query happens, since you start the race, you can actually get more than 1 reply in pretty reliably. In fact, you can get more than 100 replies in pretty reliably. So the entire philosophy of the system was just broken from the start. So what should have happened? What should have happened when the bug was found is nothing. No important system should have been vulnerable. As Halvar Flake actually said, "I fail to understand the seriousness with which this bug is handled, though. Anybody who uses the internet has to assume that his gateway is owned." I wish the world was as smart as Halvar. It would make things a lot easier. Unfortunately, it's not the case. Not to repeat all the slides, but secure systems are depressingly rare in the field. Most things don't even bother to be secure. The vast majority of the web is over HTTP. Email, which has the highest sensitive information to total lack of cryptography ratio of anything in information technology. And, oh, by the way, you know, there's more to networking than web browsers. There's like these other applications that also use sockets. And they all suck. Of course, you know, not to, you know, let's talk about SSL. Most of those things that try to use SSL, yeah, they fail pretty miserably. When you actually scan the internet, you find about 41% of SSL certificates out there. They're self-signed. They're not even trying. Their client's like, who are you encrypting to? I don't know. Non-browser network applications that use SSL just don't care if the cert's signed by anyone in particular. They're encrypting to someone, I don't know who. There are some pretty scary implications of this. Automatic updaters are non-browser network applications that assume DNS is safe. They assume quite incorrectly. There's a fantastic video put out by Francisco Amato with his tool EvilGrade. It just demonstrates owning the Java updater. SSL itself used email to authenticate its receivers to determine whether, I don't know, I should be able to get a cert for verisign.com. And forgot my password systems, bypassed authentication entirely. Now, I don't think people have fully grasped how significant an authentication bypass through forgot my password is. So I thought I'd step through a little demo. And if you've been watching my Twitter stream, this is what I've been spending all day trying to get to work just right. So we're going to go ahead and spin up a little bit of a victim Drupal site. This is frontend.doxpera.com. You know, it's my little collection of Fresh Prince of Bel-Air lyrics. And we're going to create an account on it. And we're going to force an email to be sent to a test domain, this helloccc.docsdns1.com. Now, that's going to cause the mail server that backs up my web server to go ahead and send an email. That's going to cause the DNS server that backs up my mail server to figure out where that email is supposed to go. That's going to cause me to see who the name server is and what ports it's using. So now I go to my test server and I see, oh, okay, well, the IP address is 209.40.204.174. Would be a shame if someone were to poison that name server. Now we need to have a name server that says, if anyone were to happen to come to me, clearly they want to send me their traffic and their email. Now we go ahead and just, you know, use Metasploit. Let's go ahead and grab all of doxpera.com as per this particular name server and redirect it to our attack box. Now we forget the password of the admin. Well, what's his name? His name is apparently Little Bobby Tables. What's his password? I don't know. I'm just going to say I forgot. And it's going to send me an email. And you know what's going to be in there? Little Bobby Tables. A request to reset the password for your account has been made at Drupal. Please click this link. Hey, it wanted to know where to send it. It asked DNS, who is the mail server for this particular administrator? Said, no, yeah, that would be me. Sweet. So I go ahead, I enter the administrative interface, and it's like, this is a one-time login. It's going to expire. Click this button to log into the site and change your password. You know, apparently this can only be used once. Yeah, so we're going to go ahead and post some content on this page. And I don't know if you can see it up there, but I'd like to highlight post content input format PHP code. Yeah. Title, you got pwned. System, you name A. That's right. Why the hell did that work? No, I'm serious. I mean, why? You know, passwords. You know, we can forget our passwords and have them mailed to us. Admins have passwords too. Admins forget. Admins have code execution rights on pretty much every content management system out there. I'm not just picking on Drupal here. This would hit Drupal, would hit WordPress, would probably hit Joomla, and pretty much anything else you can find out there. One generic category of attack, and that thing's going to get code execution all over the place. Now, just to be fair to Drupal, they're totally on top of this. They're building a detection interface. They're pretty interested in all of this stuff. But really, is this Drupal's fault? If there was a code execution flaw in the Linux TCP stack, would it be Drupal's responsibility to say, wait, you're running on Linux 2.6.189.3. This TCP stack is vulnerable? No, because it's not a bug in Drupal. It's not a bug in the web server. It's not a bug in the mail server. You got to go all the way down into the name server. But that one bug traverses all the way back. So now we just received a code execution equivalent token over email. So that's the seriousness of which this bug is handled. Why did this work? Why did this happen? Clearly, this is the fault of passwords. No, really. I mean, without passwords, there would have been nothing to forget. With nothing to forget, there would have been no reminder email. Without email, there would have been no dependency on DNS. And without DNS, there would have been no exposure to cache poisoning. So clearly, we need to stop using passwords and only use SSL client certificates. Who the hell here wants to use SSL client certificates? That's right. They suck. Okay, if you don't understand the problem, you're not going to find the solution. We have some bad habits in the security industry. Sometimes we'll make an appeal to morality. Well, if you were a good programmer, you'd use SSL client certificates instead of passwords. You could make an appeal to intelligence. Well, if you were a smart programmer, if you just knew how to write your code well, as opposed to all these monkey coders, you'd use SSL client certificates instead of passwords. Now, this approach is emotionally great for us as security engineers because it makes us the good guys and it makes us the smart guys. Yeah, you know what? I've spent a lot of time around people who build complicated systems. Takes them 2 years to build it. Takes us 2 weeks to break it. That means we have the easy job. Look, neither argument on morality or intelligence is compelling at all. SSL client certificates are awkward and expensive to manage and fundamentally fail a ton of critical use case scenarios. Passwords scale, and that matters. If you have a system that scales, people will use it, they will deploy it, they will build their businesses on it, whether or not it meets any sort of security purist approach. That's just the reality of things. And the number of hands that came up with people saying, I would love to use SSL client certs, is the reason why. Now here's the deal. It's not just passwords that scale. DNS does as well, like nothing else. Who here is familiar with the concept of federation? So, definition of federation, the formation of a political unity with the central government by a number of separate states, each of which retains control over its own internal affairs. Put another way, Microsoft does not trust Google. Google does not trust Yahoo. Yahoo does not trust CNN. But all three of them share a single namespace, the DNS, and all control completely operations within their particular namespace. This is hard. This is really hard. First off, it requires technology. The synchronization of distributed database is a classically difficult problem, but it's more than just a technological problem. It requires groups that are set up to absorb new information and new records and new delegations. It requires human factors. It requires registries and registrars. It requires an IT guy in your organization that you can talk to say, hey, I got a new box, it's at this IP. Stick it in the namespace here. And that needs to work. And it does. Because DNS came first. Because DNS has been around since 1983. How many of you weren't around in 1983? I just happen to be curious. You know? Seriously, like, this thing has been around for the entire history of the modern internet, and even long before that. The first mover advantage has made it the source, the only source of successful federation. That's not to say it's the only technology that federates, but oh, it's a little obvious how everything else that does need to federate pulls DNS in when they need to do it. Consider email. Email needs a way to determine which server it sends its data to. Does it deliver an email to one location or another? How does it do that? It goes to DNS. It does a lookup for the MX record to find out which server in this particular gets this chunk of the email namespace. The web has the same origin policy, quite possibly the largest advance in security technology of the last 15 years. It, too, goes ahead and turns DNS names into identities, which have ACLs associated with them. Even SSL, even X509, the ostensible, by design, federated ecosystem. You know, let's take a look at this for a second. First of all, it's not very reliably federated. Which root CAs do you trust? You know, how many people have ever used wget and it's like, I don't know, this particular wget supports this root CA, but not that root CA. It's not particularly coherent. It's also not very federated. Wildcard certificates are difficult to acquire and actually unreliable amongst clients. So there's constant cross-company interaction required for each new server you spin up. You got to go ahead, talk to someone outside the company and be like, yeah, I need another cert. Yeah, I need another cert. And shockingly enough, only the machines that really absolutely massively need certificates are the ones that get them. And it's not actually independent of DNS either. When you look at common names, one of the things you find is, hey, what is in the common name? What is the declaration of identity that an SSL cert is declaring? 9 times out of 10, that's a DNS name. That's how they went ahead and built out their system. The funny thing is, it's not that it's impossible to do federation without DNS. It's just without DNS, it's either, you know, maybe a small, maybe a large company, and it's probably 1,000 times more expensive at least. And so that's why it stays so small. Now, I'm not kidding when I say everyone federates with DNS, because all the technologies I just named are themselves built on. Password resets use email, so the passwords only go to the user that owns the account. OpenID uses the web and its same origin policy, so different sites can use the same authentication server safely. SSL uses email, so that only the user that controls a domain can acquire a signed certificate for it. Everywhere you look, when you get down to it, the federation comes from DNS. But there's a problem. And it's pretty simple once you look at it. DNS tells you how to get there. It tells you what the address is that you need to use through all the various quirks and delegations that are possible. But you know what? It tells you how to get there, but it doesn't tell you what to expect when you arrive. It doesn't tell you who you're going to see. It is the worldwide distributed, fully federated database. It reasonably secures everything going into it, but it offers no assurance on whatever you get back out. Now, in theory, what this would mean is that because DNS doesn't secure its content, nobody would possibly treat its payloads as security critical. That would be nice, but it's not real. Reality is, it is the only thing that can scalably tell you where to go. So people are just not caring that it doesn't tell you who to expect. Take a look. Email imports DNS. Email knows where to go, but not who to deliver mail to. The web imports DNS. The web knows where to go, but not if an ISP has changed anything. Password resets import email, which imports DNS, which knows where to go, but not who it's necessarily giving that admin token to. DNS's inability to authenticate replies surfaces as a failure to authenticate in system after system after system. Now, we can deny that these systems exist. We can insult their authors and call them bad programmers. We can pat ourselves on the back for being so perceptive, or we can start dealing with our inability to authenticate. Now, it turns out, interestingly enough, that our problems with authentication are fairly extensive. In fact, they are arguably the defining factor of many of the major flaws of this year. Mike Sussman, who I just actually met a couple months ago, interesting guy, started playing around with SSL VPNs. Now, this software has no other purpose but to prevent bad guys from reading your traffic. That's what they do. That's why they're bought. That's why people spend money on them. But guess what? They don't actually check if a bad guy's intercepting the traffic and make sure that not to send traffic to them. They'll give the traffic to anyone. Mike Perry built a little tool called Cookie Monster. So the interesting thing about Cookie Monster is HTTP is tunneled over SSL, and you receive cookies over it. And those cookies are authentication tokens, like that thing that just got mailed through Drupal. And it authenticates access to https www.bank.com. By default, those authentication cookies will also go to http www.bank.com. Now, you can change that. You can change the default with a non-standard tag called secure in your cookie. But as Mike Perry found out, almost nobody does that. And then there's Francisco Amato, Evil Grade, the automatic update manipulator. One would think that anybody who went out on the internet and said, "Dear Internet, please give me arbitrary code to execute," that they would actually authenticate the code received. No. It wasn't even like small guys. It was like Java, iTunes, OpenOffice. Yikes. Two more. Luciano Bello's Debian random number generator, one of the cooler bugs from the year. Yikes. You know, it's not a private key if there's only 1 out of 65,000 of them. Amazing how 1 out of 65,000 just got plucked out of the air once again. This is the actual coolest bug of the year. I think it's cooler than my bug. How many of you guys know about the SNMP v3 bug? God, I love this. So, you know, you gotta have, I'm gonna bastardize the bug. Imagine if you had a website that was asking your password and you didn't know it. But you could say, you know, I can't give you my full password, but I bet I can give you the first letter of it. Is that okay? Yeah, it was that kind of bug. God, that was glorious. So, you know, our common trait here is that flawed authentication is the unifying theme of 2008's major bugs. From SSL to Cookie Monster, from SNMP v3 to Evil Grade, we just don't know who we're talking to, and it's getting us in a heck of a lot of trouble. We just don't know. So there's some common traits of all the bugs that I just told you. The first major common trait is they're all so amazingly simple. DNS's TTL defense can be bypassed with alternate names. Authentication cookies received securely will be sent insecurely. SSL VPNs don't care who they deliver packets to. Large amounts of software don't care who they get their updates from. These are not complicated bugs to understand. A collection of a few words and you can build a repro. Okay, we don't have that in a lot of other things. The flip side is these bugs are horrendously complicated. Now I was talking to a friend of mine. He's a release manager at a company that has to deal with a whole bunch of bugs that y'all find. You know what he told me? He looked me straight in the eye and he said, "Dan, I love buffer overflows. They're so simple to fix. No one depends on them. No one builds entire companies that need that buffer to take more memory than it actually has. You don't need to collaborate with any other companies that suffer from them, build mitigation plans, multi-phase systems. You find a bug, you put a stupid little wrapper around it to say, make sure this number isn't too big, and you move on. And that's not design bugs. None of those bugs I just told you is particularly trivial to fix. Most of them are still there. The fourth common trait is that the bugs I just told you blend, and they blend really well. This is, by the way, why it's ridiculous to compare who found the bigger or better bug. There's no such thing as a bug so good, another bug can't actually make it better. So, DNS and SNMP v3 give you a pretty good basic for the rest of the things to be directly exploited. DNS and SNMP v3 let you become man in the middle. So, when Cookie Monster is man in the middle, it can go ahead and impersonate http www.bank.com, thus getting the authentication cookie. When you have Debian with its generated certificates, you can use DNS or SNMP v3 to impersonate SSL endpoints. And of course, as was in the actual Evil Grade demonstration video, you can use DNS to provide false packages for Java. Interestingly, DNS also lets you exploit SNMP v3, and I thought this path was kind of cool, so I'll kind of mention it. Well, so DNS, so last year we were talking about how Java has access to sockets, make network connections, right? So DNS is, we had to lock that down because you could kind of, I don't know, get behind firewalls and own a bunch of machines. So they went ahead and said, okay, we're only going to allow you to connect to addresses when DNS says it's okay. Well, we own DNS, so DNS is saying you on that browser can make a network connection anywhere you want, TCP or UDP, to which I say, UDP? May I please have UDP access to every Cisco network device behind your firewall? And Java says, sure, no problem. And then the SNMPv3 bug comes. So again, I mean, really, it's ridiculous to compare bugs. They work well together when they're design bugs. Fifth common trait is that they are often found in old systems. The DNS bug was in a spec from 1983. The cookie spec was from the mid-90s. SSL requirements have been known from the dawn of the protocol. And the v3 spec has been around for years too. Age does not predict quality. In fact, frankly, we didn't used to take care of security that well. I don't even know if we do now, but we really used to do it pretty badly in the past. The sixth common trait is that all these bugs, all these authentication flaws, are very, very slow and expensive to repair. DNS Fix is probably the largest simultaneous patching operation of all time. It was an amazing amount of work just to minimize the disruption from the fix. I think we did a pretty decent job, but this was something that was 2 days to find the bug and 8 months to fix. And this was a simple fix. No one depended on ports not being randomized. The patch rate was a lot higher than our wildest dreams. Paul Vixie, in his experience with DNS patches, and he's been through a few of these, say the least, he was expecting 50% coverage after maybe a year. We hit 75% after about a month. So that was cool. I wish we had that for all the bugs I just described. You know, major sites are still struggling to adapt to the cookie monster attacks. SSL VPNs are still widely broken despite public knowledge of their flaws. So it's not like these bugs fix themselves. I have an interesting theory. And I'm going to tell you straight out, I don't know if it's right, and there's no real way to know. But here's a historical what if for all of you. What if DNS had been secure from the start? Would all of these design bugs have actually happened? SNMPv3 and the Debian bug definitely would have. But what of the SSL VPN issue? What of Cookie Monster? What of Evil Grade? Why are SSL VPNs insecure? Now, I'm going to be honest with all of you. My original reaction to finding out that SSL VPNs, which had no other purpose but to prevent bad guys from reading the traffic, that they weren't actually checking for bad guys, okay, I was pretty pissed. I was mortified. I'm like, who are you people? Why would you possibly sell a product that doesn't even do the one thing you're designed to do? I kind of blamed commercial realities for it. Then I started listening. Well, we have to ship test gear to our customers. And you know, it still has to work after they buy it. How are customers supposed to actually get SSL certificates onto their devices? You know, it's an interesting question. The present system for securing SSL for devices requires interactions between 3 companies: a device manufacturer, a customer, and a third-party root certificate authority. Okay, guys, intercompany interactions are expensive, especially when you need to do it on every single purchase, especially when things will actually still work if you don't do it. And yet, every single one of these devices, for the most part, maybe 90, 95%, they may not have an SSL certificate, but I bet you they're showing up in the company's DNS tree. I bet you that someone actually was able to do enough administration on that device to get that thing in DNS because no one wanted to be dependent on raw IP addresses. Anyone ever deploy a bunch of machines on raw IP addresses and then need to readdress? This sucks. You don't know what's depending on the old addresses. You can't update them. It's a nightmare. So here's a question. If DNS had been a secure place in the first place to put certificate hashes, might SSL VPNs have just told people, hey, you know, when you're putting the IP address in DNS, just put this hash too and you'll be done. Maybe this problem never would have happened. What about HTTP cookies via SSL? Why would it be that the same authentication strategy cookies get shared between the secure and insecure side of a site? Well, it's because there is a secure and insecure side of a site. Why is there an insecure version of any major bank? Legitimate question. You know, the fact is that there are some scalability issues inherent in SSL, and there's also the fundamental problem of there is no good way to tell a web browser there is no HTTP version of this site. If you're going to come to me, always be secure. We don't have a way of doing that right now. So what you see when you actually look on major sites is they'll tell you, oh, you came to the insecure version. Would you pretty please upgrade to the version that actually has some cryptographic assurance? You'll get a nice pretty lock. Amazingly enough, you know, if you're a DNS attacker, you just don't do that. You're like, no, we phased out SSL. It was slow. Can I have your account number? Oh, yeah, we got to authenticate you. Can I have your social as well? Thanks. You know, what if we had a secure and scalable way to declare that a site was HTTPS only? What about automatic upgrades? You know, an automatic upgrade over SSL would have almost every security property of Windows Update. It'd be missing one. You wouldn't be able to have a magic signing box offline in a vault with two-party, you know, magic tokens, you know, this crazy stuff no one actually does. So you wouldn't be able to do that with SSL. But you would actually be able to just connect to a server, download a patch, and install it, and you're done. It would also be a lot slower, though, because SSL negotiation is not the fastest thing in the known world. There is kind of a very simple rule. It has to work. And you know, doing automatic update on millions of machines with SSL would not actually work too well. And so people distribute their updates over HTTP because it scales. And they say, well, we'll go ahead and we'll sign the package. We'll apply a signature. It'll be great. It'll be wonderful. And you know what? They keep screwing it up. They don't check to make sure you're upgrading to a new version. You know, hey, you know, you're on version 6. No, I want you to install version 5. It's signed. They'll have like different packages, you know, other software from the same vendor, or the wrong signing key, or they don't actually check the certificates. There's a bunch. Here's kind of the rule. When you're building an automatic update system, on day 1, you go out to the internet and download and install new code. On day 50, only you get to do that. The 49 days, so does the bad guy. So guess what? Everyone stops on day 1. Just gets the bare minimum necessary to go ahead and update their customer's code. You know, what if there was a secure and scalable way to distribute the final hash for new versions of packages so that you just looked in DNS, saw the hash, and you were done? What if we had a secure and scalable place to put PGP keys? You know, maybe. I'm just saying, maybe we'd finally have secure email. It's 2008. I've been hearing about this since the beginning of whenever I was using the internet. Okay, I got to level with you guys. I've spent the last year dealing with PGP. PGP added an average of 48 hours to my being able to communicate with everyone, and it had maybe a 66% success rate. This is not working. So, we keep blaming those evil business guys who just won't fund it because they're bad people, they're business guys, they're stupid people. You know what? This is a crutch. We have been blaming the business guys for what is ultimately poor engineering. The systems we are trying to build to make up for the fact that DNS is insecure are resource intensive and repeatedly are failing to scale. Now, we spent the last year finding design bugs that break authentication. Maybe there's something fundamentally missing. Maybe there's some reason why we keep finding all of these failures over and over and over again. I think we're missing a part. You know, perhaps DNS shouldn't be at the heart of authentication. Perhaps that's the way things ought to be. But you know what? It is. And maybe it's time we start treating it that way. Now, there are some people who will have the attitude, and it's fairly common, that says, well, no one should put anything but addresses in DNS anyway. DNS was not designed for all of this crazy stuff. You crazy kids, what are you doing putting all this stuff in DNS? It's not secure. Well, the jig is up. And the jig is up because of federation. Federation means You can put in DNS whatever you want. It's your namespace, it's your content. You can put whatever you desire in there. And people are. They're putting anti-spam text records, they're putting VoIP directories, they're putting IPsec keys, they're putting SSH fingerprints. How is SSH fingerprints in DNS supposed to be secure without DNSSEC? HTTP was never designed for dynamic content. It was designed for static web pages that were at file lengths. If you wanted dynamic stuff, maybe you made a post, but that was it. But that's the reality of Federation. In Federation, no one gets to tell you what you put on your server. And people are putting authentication critical stuff in there. Might as well be able to do it securely. So what's it going to take? What do we have to do? Well, the first thing to do was to put out the fire that, frankly, I sort of set. DJB started it, and, well, it kind of blew up. Next, we have to figure out how to make DNSSEC scale, because it doesn't yet. And finally, we have to start migrating new applications to be aware and able to use it. So let's talk about the putting out of the fire. How did this happen? How did we get from lots of red showing lots of vulnerable machines on July 9th, 2008, to lots of green and a little bit of yellow on August 3rd, 2008? How did that happen? Because you know what? Systems don't fix themselves. Well, first off, Vixie. You know, Paul Vixie gets a lot of crap. Paul Vixie's been writing code for many, many years. And yeah, you know, a lot of his code has had bugs. But you know what? He wrote more code than you for, I'm pretty sure, all values you in this room. And if you're going to write code in the 90s, of course it's going to be insecure, because no one was writing good code in the 90s. Now, DJB was writing good code. How is his release engineering? Crap. And that matters. You know, every time I have ever written something for release, I have spent more time making that thing build on platforms and packaging it up and dealing with support than I ever spent actually going ahead and writing the software to begin with. Saying that release engineering is a problem that, oh, it just does itself, it's just not true. I mean, there are things that are facts, and that's not one of them. DJB wrote some fantastically secure code. Did he package it up in a format that anyone could really build on it? No. No, he didn't. So, Paul has been dealing with the DNS industry for the past 15 years. Dude knows everyone who actually matters in DNS. The only reason I was able to get all the people in a room is because they've been dealing with Paul for a long time, and for Paul to say, oh, dear God, remember that thing from DJB that we ignored? Oh, we probably shouldn't have done that. Oh. So, you know, good amount of humility on his side. He pulled in the critical engineers from all across the industry. We met in person. You know, I got to level with you guys. Email is great for lots of things. Making decisions is not one of them. The problem is that an infinite number of factions can break off, and an infinite number of people can join in, and it is just not good for keeping secrets or ultimately fixing stuff, or at least coming to a conclusion on how things will be fixed. Paul actually brought in the engineers with decision-making capacity. First of all, the fact that there even were engineers with decision-making capacity was kind of fantastic. That's how we kept the politics out. That's how it happened at the end of the day. The third thing is we agreed to synchronize our fixes. Look, the bug class is trivial once you recognize that TTLs are insufficient mechanism for creating security. We basically realized if anyone actually went public with their fix and why they fixed, everyone else's customers were going to get hit. And it was just too much. So we basically all agreed, we do this. We're doing this together. We're doing this as a group. We're going to synchronize it. We didn't think about it that much like it was a particularly big deal at the time. But as we got closer to release, like, wow, Microsoft is patching at the same time as Cisco is patching at the same time as Linux. Cool. So there were some ground rules for the fix we had to choose. First ground rule is that we had to secure all names, not just most. the thinking was is that any particular names, no matter how obscure, that would be a little less secure because, I don't know, their natural TTL was low or because they were in a single level domain or whatever. Anything we missed would just get hung over us at the next black hat. Second thing is we had to secure all the authoritative name servers, not just those that opt in. In other words, we wanted to do this purely from this perspective of recursive servers that go out to the internet. The way we looked at it was simple. Look, suppose you had a fix that depended on having both the servers that go out to the internet to look something up and the servers that receive these requests and send replies. Who goes ahead and patches? The authoritative guys say, well, no one's deployed the recursive fix. And the recursive guys say, well, no one's deployed the authoritative fix. And nothing actually gets fixed. This is how these things happen. So we wanted a solution that was purely at the recursive servers so that when you deployed it on the recursive server, every single system, every single name you went out to would be safer. Now, DNSSEC does not have this property. DNSSEC actually requires the upstream servers to do modifications. But there are lesser things that can happen at the upstream servers. You can have cookies or other modifications where when you go to this other server out on the internet that hosts the names for Google or hosts the names for Yahoo, that this other server can have some extra information that it reflects back to you. The problem is that none of these approaches are actually secure unless the root server and the COM server signs up for them. The reason why is, oh, your server at foo.com is safe. That's fine. I'm going to tell your name server that your box doesn't exist, that your box is actually my box. So you're going to, all foo.com comes from me. What was that? DLV is another mess. Coming up to me later. The third thing is that we must not, hey, I'm a DNSSEC supporter and we will talk about that later actually. So, third requirement is we must not alter the semantics of DNS. If 1% of names just stop resolving, no IT administrator in the world would have deployed the patch. It doesn't matter if you say, but they're not important names, but they're these really obscure sites out in Russia, it's complaints. And you know what happens when DNS goes down? It's so deep in the stack that you're looking at 12 to 15 hours of debugging before you even figure out that it was a DNS issue. This is why DNS cases are always so expensive, because it's completely obscure. Why did 5% of the machines suddenly lose access to this database server in Kazakhstan? What? Seriously, anytime I get like a completely inexplicable fault, well, okay, it's me, so I think it's DNS, but you should think it too. So the easiest fix, and arguably the correct fix, was exactly what DJB told everyone in 1999. I understand why people did not want to do source port randomization back then. It's not elegant. It's slow. It's difficult when there are other services on the host. You get these port conflicts. It doesn't play at all well with firewalls. So firewalls end up taking your nicely randomized source ports and just kind of fixing that. Makes it more secure. No, big old mess. Not actually on this list. There are a bunch of kernels back in 1999 that really couldn't handle lots of open sockets at the same time. There were also a couple kernels in 2008 that also couldn't handle it. Dear God, guys. Be that as it may, in terms of just getting the actual code built, given the findings that I showed up with, we basically all agreed, yeah, that may not have been the right thing to do then. It's certainly the right thing to do now. Meets the ground rules perfectly. Secures all names equally. There's no sort of name that doesn't have a port or transaction ID associated with it. It secures all name servers equally. Even the COM and root servers have to go ahead and reflect your UDP source port back. They have to do it because it's fundamental, just rules of how UDP works, rules of how TCP/IP works. It was a brilliantly elegant solution that DJB came up with. And it does not alter the semantics of DNS. There's no record that would have been returned before the patch that wasn't returned after the patch. It's also very simple. Every other fix, big ol' mess. Do not underestimate the value of simplicity when telling people how to fix their flaws. We knew at that meeting, we actually met at Redmond. Microsoft was very nice. They hosted us. We knew sitting in that conference room, wow, we could do all these crazy things with rules on what names get to override all other names. The odds that even one of us would get it right, let alone all of us in the same way. We knew the odds of that, let alone in an interoperable fashion. We knew the odds were 0. 0 is very low. None. Not going to happen. DJB was right. There are some alternate strategies that are interesting, that are even being explored right now. This is the next generation pre-DNSSEC fixes that are being explored. Lots and lots of people want to go to the good old days when we thought the TTL worked, where we thought, well, okay, 1 out of 65,000 isn't a lot, but maybe we can make it that, fix the flaw in that beautiful, brilliant model. Yeah, at the point you have 15 bugs in a security technology, maybe it's time to move on to something new. Here's a really fun way around the TTL that actually got shown to me. If you go to a name server and you tell it, I would like to look up www.google.com with record type 1337. This does not exist, but it's totally elite. Name server goes, well, I've got an address. I've got like an IP address for www.google.com. But you know what I don't have? I don't have anything leet for Google. So I better go see if Google has anything leet. So he goes off to Google. And meanwhile, you reply with a whole bunch of messages that say, nah, there is no such thing called www.google.com. Just doesn't exist. Eventually, you'll win. Eventually, you'll get a reply back. But guess what happens when you get that reply back? Name server says, well, I guess there is no such domain as www.google.com. Throws it all away. TTL bypassed yet again. I'm not saying you can't fix each one after each one after each one. It's just at some point you have to admit, man, this stuff doesn't work. It's a useful approach for defense in depth, but it's never, ever going to be comprehensive. You will break the semantics of DNS. You will make the wrong record come back. You will hit that 1% failure rate trying this path long before you will do any reasonable dent on the ability of an attacker to hijack names. All the fixes that try to limit what you actually retrieve are all retreats back to the old TTL mechanism. They're all about, well, if we can just prevent somebody from being able to overwrite www.google.com, we'll be safe. I don't think it's going to work. It might be an interesting component, but it's not going to be the answer. There are some other tools at our disposal. DNS theoretically can operate over TCP. In reality, TCP is apparently a performance death from which there is no return. Apparently, name servers really don't like it if they have a whole bunch of TCP connections. There's attack mode. This is what I was looking into a while ago. You know, attacking DNS after source port randomization is in place, after my fix. All we did, was make it 65,000 times harder to attack a name server. So all of the badness is still there, it's just 65,000 times harder. Well, you know, someone might sit there and send you billions of packets, and then, you know, you're going to fail, right? Well, billions of packets are many things. Subtle is not one of them. So I was thinking, why don't we have defenses that only come up when we know we're getting hit with billions and billions and billions of packets? But what do? What is the actual defense that we take? It's a hard question. You can't block. You can't block entirely. DNS requests can be spoofed. It'd be a trivial way to go ahead and say, yeah, I don't want this name server talking to that name server anymore. And indeed, all the people who have rate limiters per IP to get around these attacks, yeah, all you do is flood with a whole bunch of requests. And you can say, yeah, you know, I really don't think that this ISP should be able to reach that bank. Which actually opens things up for a whole bunch of other attacks. There's a couple other tools that can be mixed in. Double and triple resolve. So, you know, you have multiple queries for the same name. Hopefully, you'll get overlapping responses back. So nice, hopefully. It doesn't actually happen as often in the field as you would like. You know what you don't get to do when you fix DNS? You don't get to break Facebook. So it's good for attack mode, but bad for all these content distribution networks like Akamai and Limelight and so on. This is what Nick Weaver calls volatile records, and they are a problem. Final thing that people are looking into is called OX20. And this is the case sensitivity bit in ASCII text. DNS is case insensitive but case preserving. Meaning if you look up www.google.com with weird caps, you'll actually get a resolution through. And the response will actually contain the case that you originally described. So you might say, well, great, I've got all these extra bits. I got uppercase, I got lowercase. I'm going to make sure they all come back okay. Some name servers don't support it. But the bigger problem is names like A1.1111111. There's no such thing as an uppercase 1, so you only get an extra bit. Should there be a midpoint fix? Should there be something before DNSSEC happens? I don't know. Maybe. There might actually be a combination of fixes that once assembled actually kind of works. I don't know. It's ugly and it's messy, and it sure as heck was not something we were going to try to do 18 engineers in a conference room at Microsoft. So, what of the actual release itself? Most of what happened after July 8th is very public, so I don't want to actually go in too much depth on it. But there's a couple things I'd like to speak to. First were the notifications that we actually did to people, and second was the testing app, because I think that was actually kind of cool how we built that out. So, I had a question for you guys. Raise your hand if you feel like it. How many people in this room have ever been asked to steal a bunch of credit card numbers? One. How about run off with a laptop containing gigs of personal data? Anyone? Extracting data from the servers of a large multinational? Okay, for this next one, be honest. There's no way anyone's going to trace it back to you. How many of you have ever been asked to break into someone's Hotmail account or Gmail or Yahoo? Yeah, that's right. So this is why I spent a good portion of July on the phone with Google and Yahoo and eBay and MySpace and Facebook, because there ain't nothing people want to break into more than personal email. The other group that we were really worried about were the SSL certificate authorities. Domain validation is embarrassing. The idea behind domain validation is you go to a website and there's a little lock. And little lock says, you're at www.bank.com, and you can tell because there's a lock. Well, do you ever wonder why the bank was able to get the lock, but you yourself couldn't put up a server? Well, you see, what happens is that the bank goes to VeriSign and says, we'd like a little certificate. We'd like to do the lock. And they say, well, how do we know you're you? How do we know you're actually a bank employee? You could be some guy. And then it's, well, why don't you send me an email? Which we own. So, Microsoft handed me a list of every single certificate authority in the world. And I spent the next month fielding phone calls from Finnish government authorities. It was awesome. So, finally, we considered auto-updaters. Frankly, we kind of underestimated just how many of these were actually broken in the field. We got LinkedIn fixed really quickly. They had a little toolbar. It's apparently really common in corporate environments. I mailed security at linkedin.com. I got a phone call back in 20 minutes. I approve. Incident. Yes, you did. But yeah, I actually really want to point out, every company should have a security at email and have someone whose job it is to actually receive and check that mailbox. There were, I'm not going to name names, but there were companies I had to take some pretty extraordinary measures, top 10 web properties that I was on the phone with at Black Hat 17 hours before my talk to get them to fix. So security at unnamedcompany.com would have been much nicer. And yeah, Francisco Amato did a fantastic job with Evil Grade in demonstrating that we had underestimated the severity of this problem. The other thing we did, and this actually turned out far more interesting than I actually expected, was built a tester. So I am many things. I am not a web designer. That I can say is Crystal over there. And Crystal actually helped me build out this entire web interface for go online and see, is your DNS safe or not? By the way, this is the DNS for the Park Inn, and I'm happy to report the Park Inn has been patched. That's actually a rare pleasure to be able to say, I'm staying at hotels all over the place, and for some reason they're all secure. So we had this web-based tester, and there were a few. How am I doing for time, by the way? Sweet. We're doing great for time. I even have time for questions. So there are a few things missing from this tester that people kept mailing me requests for. One of them, and probably the major one, was, how come I can't put in the IP address of my name server? And the answer is, because you have no idea what your name server is. Don't kid yourself. Look, people have no idea what name servers they use. It's set once, it's forgotten about. Maybe the name server is behind a firewall. Maybe the name server is set up in some kind of weird, dynamic, auto-clustering, magic. Like, the weirdness that actually happens with DNS is astonishing. I once made a graph of all the DNS relationships. I swear to God, it looked like the Human Genome Project. So what I ended up doing was saying, look, somehow this web browser found my website. It had to use DNS to do that. Whatever name server you use to find my website, I'm going to test that name server, and you're going to help me do it. I'm going to bounce off your browser. I'm going to have your browser do the necessary lookups. And this led to a very funny thing, actually. People said, well, if my DNS is poisoned, I might not actually be able to reach www.doxpera.com. So there's the way I can test my DNS off your IP address. I'm like, wait, if you're coming to my IP address, you're not using DNS, so how are you testing your DNS? Hello? Anyone? Dozens of mails of that type. So the second reason why I had a web-based tester was I really wanted customers to be involved with this fix. One of the things you hear a lot is that there's no customer demand for security. And I think a lot of that comes down to there's no customer awareness. There's no way to know, am I vulnerable? Is this something that affects me? Is this something I should even know about to make a determination of? So I had this tester as accessible as possible. Just a simple button, click check my DNS, and it will go ahead and tell you if you're having issues or not. And customers could go ahead and protect themselves by calling their ISP and providing demand for a fix. Or they could go ahead and protect themselves by using one of the free DNS providers like OpenDNS. However the customer wants to protect themselves, and if they don't care, they do nothing. I was just looking to enable. So how the tester actually works, some technical details here. I had a little bit of fun with this. The way the tester works, you'll notice these big, huge, ugly CNAMEs that have a bunch of noise. And if you've been ever looking at them, you might have been wondering what they are. So here's the deal. In DNS, when someone asks you a question, you can reply with, I don't know, why don't you look up this other name instead? And they can come with you the other name and go, I don't know, why don't you look up this other name? And keep moving them in a loop. Well, each of these names contained inside of them, encoded in base64, what the actual IP address, port, and transaction ID that was used for the previous request. So I didn't need to store in a big database all of the previous requests that I was receiving. It was just, oh, you did a lookup with me with no information? Here, why don't you do 1? Oh, you did one with 1? Here, why don't you do 2? Here, 2, 3. Till 5. And at 5, I would actually decode all the information, dump it into somewhere where the web server could read it, and you can actually see it yourself. If you generate a random number and do get on http something.docsdns1.com/fprint/ whatever your random value was, you'll get back this text string, which was originally designed to be read over JavaScript. And it'll actually tell you, yeah, though that series of requests you did, here's when it happened. I leak my time, I'll live. It was, these were the IP addresses, this was the port, this was the transaction ID, and so on. And then through JavaScript, I parse that and say, okay, well, your ports didn't randomize, or your IP address was a particular IP, and so on. And that's how it worked. It was pretty straightforward. Now, there was a small bug at the beginning, which eventually had to get fixed. So originally, when I moved you around in this loop, I would say, please keep hitting this particular name server please keep hitting the same IP address over and over and over again. And I thought that was fine. Well, it turned out, after we realized all the firewall issues, some people built firewall rules that said, okay, will randomize ports as long as the IP address changes. If the IP address stays the same, well, it's not leaking the port to anyone. We'll just let it keep using the same port over and over and over again. So like, cool. Wait a second. That means my tester doesn't see the port changing, which means my tester is giving false positives, which means I have some unhappy ISPs on my hands. So went to ISC and said, hey, I need a host. I need to have 5 IP addresses. And the replacement was, when you go to the first server, it says, no. Go to the second server on a different IP. You go to the second server, it says, no. Go to the third server on a different IP. And each of those times you get different ports, and that gave me accurate data. So that was cool. Mail. I needed to get mail into the picture. And this was a bit of an evil stunt. So what I would do was I would generate a random mail address and tell people to, hey, go send an email to this and leave this web browser open. Now what would happen was the user would send the email, maybe through Exchange, maybe through whatever. That would hit SMTP. SMTP would hit DNS. DNS would hit my little Perl script, which would go ahead and generate a file, which would end up getting picked up by a web browser that was polling for that file. So you should not try to wrap your mind around the HTTP to SMTP to DNS to HTTP to HTML bridge that I had to write for all that to work, but it did. Left undone was a bit of a stunt that I thought would have been a lot of fun. I was considering allowing people to embed a tester into their own blogs and websites. A couple people actually asked for this. Problem was that no one would actually ever support script sort, and hi guys, I'm a hacker. Could you please embed my JavaScript into your online bank? Let's talk about things that are not going to happen. So I had to come up with a solution, and the solution was actually the Billy Hoffman plan. This was fun. So web browsers are very, very restrictive on what information they will allow to flow cross-domain. Unless you go, script source to some other domain, and then it'll let anything happen. But the online bank did not want to have to trust me. They wanted to get a little bit of information out of me, whether the server was insecure, DNS server was secure or insecure, but they absolutely did not want to run my code. So how do we do this? Well, there's one really small, and by really small I mean a couple of bits per HTTP request, that allows scripting. It doesn't allow scripting across sites, but allows a few bits to move cross-domain, and it works on all browsers, and it's the image size of an image, which can be loaded cross-domain. You can't get access to the pixels, but you can find out, was that a 1x1, a 2x2, a 3x3, a 4x4? So I find this, and I'm like, man, this seems like something Billy would have worked on. And oh yeah, the dude wrote like an entire tunneling library over it. He's like telling me, oh yeah, PNG gets really annoying when you get these dimensions. You have to go to XBM, but that doesn't work in Netscape. But oh my God, that's weird with these. Dear God, man. He's like, wait, you found a use for that? I will use this stunt for a future thing, but I thought I'd document it. Maybe there's something you have for it. So now what? What do we do now? Well, we're at about 75%. We're not getting better anytime soon. There are no numbers yet on what percentage of users are actually protected by the 75% of name servers. So you could have all the users because all the major ISPs. You could have a couple of tiny, few name servers that have like 100,000 users behind them. We don't have measurement yet. Do we keep going? Are we done yet? No. All the bugs are still there. I mean, all the software I described is still broken. It's just we've kind of taped over the problem a bit, and not particularly effectively by the one fix from 1999. So, DNS is not alone, guys. There have been at least 4 bugs this year that have exposed content which, for some strange reason, is trusting that its gateway has not been compromised. DNS bug was one. The BGP bug was another. The SNMP v3 bug was a third. And then how many of you guys saw the WPA2 break that was at PACSEC a few months ago? Yeah, what happens when you break into a wireless LAN? That means you're on the LAN. You are the gateway now. And there's going to be more. Now, I said earlier I believed DNSSEC can actually be a help for this. Question is not why DNS was insecure. Of course DNS was insecure. It was designed in 1983. Question is why everything else, things that were designed like last year, why those things are insecure and what we're going to do about it. So I got a few thoughts. First off, the present deployment numbers mean nothing. DNS, like all the authoritative server modifying solutions, needs the root signed for the solution to at all be meaningful. No one's going to go ahead and do any work to deploy something that has no actual use in the field. And if you can just go ahead and attack the parent because the root isn't signed or COM isn't signed, you're done. Now, XQID thought that they had a way around this whole root and COM poisoning issue. Doesn't work. You can come find me later if you want to hear the gory details. Now, the root has remained unsigned in DNSSEC for far too long. That's apparently going to change. I apparently have something to do with that. Apparently, the big thing in the DNS world right now is automation. How do we make key signing just happen? Look, DNS scales. We know that. We've seen it do it for 25 years. DNSSEC in its normal operating mode, not so much. You know, there shouldn't have to be talks about how to deploy DNSSEC. You should install the latest version of bind and be done with it. Now, that doesn't mean that's entirely going to work. There are some fundamental requirements that make that difficult. But we really do need to get the deployment story of DNSSEC as close as possible to source port randomization. We also need to figure out how exactly we're going to interact with the registries and registrars. These are the servers that ultimately consume data to put it into the global shared namespace. These systems have no idea that DNSSEC exists, and they need efficient and elegant ways to find this data out. We need to ease the business load on them as much as we need to ease the management load for the end administrator. Now, what about DNS Curve? You guys heard about this? DNS Curve is DJB's alternative solution to DNSSEC. Be another about 3 minutes. DNS Curve is interesting. I think we have a lot to learn from it. It's based on link-based crypto instead of anything that can actually be cached. What's good? First off, it just says, look, you're going to have your signing key online. The original thinking of DNSSEC was that you only updated your DNS records every once in a while, and you could have like the key in a signed vault and all of this crazy stuff. It was never going to happen, especially not in 2008 with the rate at which we move things around. The model is far too dynamic, and admins are far too harried for offline keys sort of make sense. So DNS Curve just says, forget it. Let's see what we can do, assuming that a signing key is online. The other nice thing, the really nice thing in DNS Curve is that registrars don't have much to do. All of the chaining of security is based on the actual names of name servers. So here's what doesn't work. Well, first off, there's no code. Okay, that matters. The second problem is that it requires new crypto. You know, Dan Bernstein doesn't think that much of RSA. You know, ECC is standard, but his proposed curve is not. I mean, it's a curve optimized for speed, which is about the last thing I want to hear when it comes to the safety of a crypto system. And it's not actually that fast. I want to repeat all of those. It's not proven, it's patent encumbered, and it's not specified. It is cool. It is totally cool. No, look. Performance matters. DNSSEC was designed to not require per-query crypto operations on an authoritative server. That means if you've got a record and you're the server for COM or Google or whatever, you sign it, you return it. You're not doing crypto every time someone asks you a question. With DNS Curve, every time someone comes up to you, you got to be like, oh crap, I got to go ahead and unpack another DNS Curve blob. Okay, I got to go pack up something new. How expensive are these crypto operations anyway? Well, they're relatively fast, but, you know, DJB's sample code, I went ahead and ran it. I'm on a laptop that has capability of doing about 15,000 DNS queries per second. It can do maybe 10,000 ECC operations per second. We got to do 2 ECC operations per second for a DNS Curve operation. That means you're spending 100% CPU at 1/3 the load. No one is going to deploy this. Now, it could possibly be optimized faster, but why? You know, the larger issue, and this is the thing that I consider the fatal flaw in DNS Curve. And remind you, I have nothing but respect for it, and I think we have a lot to learn from the proposal. But there is no way to ever achieve end-to-end trust with DNS Curve. With DNSSEC, we can envision ultimately clients that do their own validation using the name server infrastructure just to cache. In other words, your desktop actually is validating every single record to see, do I have a chain from the root? And it doesn't increase load because all that stuff still uses the caches inside every name server that's out there. Well, DNS Curve says no. You don't get security unless you are directly interfacing with the DNS infrastructure. That means your stuff can't be cached. That means no one can say to you, I have validated this information, and if you'd like to see it yourself, here's what I used to validate it. Because the validation secret is not in your hands anymore. So there are two possibilities. You either abandon end-to-end trust, meaning all these applications that need to get secured don't, or you abandon caching, meaning there's 100 times increase in the amount of DNS load out there. Okay, DNS can't absorb 100 times increase. So it has a lot of cool things. I really, really like. There's a lot of DNS Curve that can actually be absorbed into DNSSEC that's going to make people unhappy, but it's the right thing to do. We have more to learn, but I don't think it's the right approach for the time. So a couple conclusions. No, we're a bit over. First, federation is hard. Everyone's been using DNS to do it. That DNS is not secure has not been stopping people from doing it. And authentication has suffered. But authentication has been suffering. It's a mess out there. DNS offers potentially a way to fix this. It is at the core of so many systems that putting a fix here has effects above and beyond. And finally, I have just one more thing. I'd like to point out that when I poisoned that name server, that Drupal installation at the beginning, that was frontend.doxpera.com. Meaning there's a backend.doxpera.com that it was getting its database from. Well, it was getting its database from until the point that I poisoned DNS. And now I had the front end going off over the internet, making a MySQL connection to my backend. Okay, we got to fix this stuff. We really do. That's what I got. Should I take questions? Okay. So thank you much. I'll be around for questions outside, but they need the room now.